Hi everybody, I'm going to make a video solving problem 6.6 in the book. First off, some general announcements. I'm actually not going to write them down, so just ignore that. People did pretty well last week. Obviously, a lot of people had issue with the trust problem. I'll make some more videos on that if people like. Also, the problem 4.4 with the house, that you had to find all the loadings and all the beams. A lot of people had trouble with this. Note that this is very, very similar, in fact, almost equal to the project. Project is obviously a lot more work. You have to basically do this problem and then do some extra things to make it into the project. There's a template for this I'll post soon, but make sure you look over this project. It's a lot of your grade. It's similar to problem 4.4, and it might take a lot of time. So make note of that, and now I'm going to just go ahead and start solving problem 6.6. You notice in your book, this is one above the homework that you have to solve, so you have to do this one for your homework. I'm going to do this one and kind of lay out the general format that makes these problems fairly easy to solve and easy to grade for me, which is awesome. So let's start out with redrawing our little figure as if we were doing our homework. It's a 1/2 inch. There to there, 4, there to there, and 6, here, there, there. Okay, so I have this weird shape. It's not a perfect rectangle, so we have to figure out what we're going to do with it. First big step is to find the center of gravity. You notice that step 1 is the entirety of one of your other homework problems, so this is just part of this problem. So now we're going to find the center of gravity. What we do is we break this thing into 2 shapes. Shape 1, shape 2. You try to break the entire thing into shapes that are easily divisible. So you want triangles, like right triangles, you want rectangles. If you have some goofy block like this, you want to break this thing into shapes that are reasonable. You know, hopefully your problem is never this bad, but you always just break it into shapes that you know the math for, and then it's not too bad. So, shape 1. The length, width, we'll call length the y direction, width in the x direction. And we'll call this our origin right here. This is important in this corner. So length width is 6 inches. Width is 1/2 inch. CG, center of gravity, in the x. It's going to be right in the middle here, so that's going to be 0.25 inches. Center of gravity in the y, 3 inches. And our area, which will be 3 square inches. Okay, shape 2, or sub area 2. Length is, forgot to draw this guy. That is also 1/2 inch. Note that I do these pretty extemporaneously, so there's some out of order things here. Length is 0.5 inches. Width is, you want to, it's tempting to write 4, but remember it's not. It would actually be 3.5. 3.5 inches. Center of gravity, x. Here's where I see a lot of people, okay, here's where I screw up. I write down the name of the column again. But here's where a lot of people screw up. You want the center of gravity, which you know is obviously in the center here, in the overall coordinate system. You don't want to do it relative to this little sub-triangle. So some people would write 3.5 inches wide, so 1.875 or whatever from here. Not correct. You want the center of gravity relative to the entire system. So that would be 3.5 over 2 plus 0.5. 2.25 inches. Center of gravity in the y, that's pretty easy. It's half an inch up, so 0.5 inches. Area, 3.5 times half an inch. That would be 1.75 inches. Is that right? Yeah, it should be right. Yep. Okay, so now we have everything that we need to know about all these shapes. This is pretty much the first step for these kinds of problems. Length, width, center of gravity x, center of gravity y, and the area. Okay, so now we're going to find the center of gravity. We know that the CG for the total system in the x is equal to the sum of basically the CGX for the areas times the actual area over the sum of all the areas. So this works out to be, for the x direction, we have 0.25 times 3 plus 2.25 times 1.75. All that business divided by 3 plus 1.75. Handy old calculator. Just short of an inch. So I get 0.9868 inches. So that means that the center of gravity in x direction is somewhere on this line right here, just shy of an inch away from the origin. So now I'm going to do the same thing for the y. CG for the total system in the y direction is the sum of the CGs in the y times their respective subareas over the sum of all the subareas. So this will be 3 times 3 plus 0.5 times 1.75, which is squared. I was not careful about leaving units through this, but I should have been. We'll go back and put it in real quick. There. Okay. And then that is inches squared, and then that's inches all over 3 square inches plus 1.75 square inches. All right, now we'll find out this. 3 times 3 plus 0.5 times 1.75, all that business, divided by 4.75. Just over 2, so 2.0789 inches. You can obviously round. I just usually prefer to have like 2 or 3 digits so I can see that the math is being done correctly. So these little sub-answers, this is where the center of gravity is in this system. So the y, 2 inches, about there. That little point right there in the overall system is where our center of gravity is. So now that I have center of gravity, see, 0.9868 inches in the x, 2.0789 inches in the y. Now we need to find the actual moment of inertia. So we need an additional property for this table that we did up here. We need to know the Ix and the Iy for these two areas. For a rectangular box for this shape, width B and height H. This is if you're bending a beam. I don't actually have anything like that shape. Actually, no, I do. It's my calipers box. If you don't have a set of these, you should buy one. They're super handy. So this is when you're taking a beam like this. It's kind of like a 2x4, and you're bending it in the strong direction. So like me trying to make a bridge like this, pressing down, it doesn't want to bend. If I hold it like this, it's actually much weaker. I could easily break the case in this orientation, so I'm not going to do that. And you can tell that because the equation for I is BH cubed over 12. Note the H cubed. That's a big deal. So if you make this thing twice as tall, like if you add a little bit extra area on here, if you go from a 2x4 to a 2x8, at least if they were the nominal sizes they say they are, you would get something that is 8 times stiffer. So twice in H equals 8 times in I. So that's a big deal. So when you're looking at a beam, and you're wondering how can I make this stiffer, adding height is a really effective way. So now we need to know the IX and the IY for these little sub areas. Let's calculate that. We have the bending in the X direction. So that is like this beam running in and out of the page like this, and we are bending it thusly, or standing on it in this direction. So it gets a little, well, I changed my mind. I'm going to do Y first because it's more intuitive. Imagine this is a beam. You're walking along it this way into the page. It's being crushed in that direction. We'll find it with the width and the height that we have here. 5 times length cubed. All that business over 12. So for shape 1, it's 9. And for shape 2, it is 3.5 times 0.5 cubed, all that over 12, which is 0.036. So notice how in this direction all the stiffness is coming from this guy. This guy contributes almost nothing. And we'll find it's the opposite for the other case. So for the other case, you switch the B and the H. So in this case, you would have 0.5 cubed times 6 divided by 12, 0.0625. Probably can't read that, can you? We'll see. I'll rewrite these in a bit. And for the other one, we would have 3.5 cubed times 0.5 divided by 12, 1.78. All right, I'll rewrite those pertinent details here. So 1, 2, we have length, width, CGX, CGY, area, IX, IY. The book has a similar kind of table thing. Whatever you guys want to use, as long as it's easy to follow, is just fine with me. The book one is pretty good, so I recommend looking it over. Remember that moment inertia is kind of odd. The units are inches to the 4th power, which may not be something that you're used to. And as you might notice, these problems do in fact take a good while to solve, so be prepared to spend some time on it. let's see, the last one was 0.5. So these are all of our properties. Now we can find out the actual moment of inertia. Let's use the y direction. So, moment of inertia, we have the, let's say in the y direction, the sum of all the iy's for all the shapes, plus their area times their distance, or let's see, so this is their center of gravity minus wherever the total thing's center of gravity is, that whole business squared times the area. So what this means is if you're looking at bending about this axis and you had a bunch of 2x4s or something like that, and you want to know the moment of inertia for all those things, suppose you just nailed them all together, it would just be the moment of inertia for each of them, adding them up. If you had two 2x4s together like that, then you have to look at the distance between the little sub-shapes center of gravity and the center of gravity of where you're bending about. I'll give one more page here. So we have this shape. And we know our overall center of gravity is somewhere around there. If we're going to look at the total bending in this direction, so like you extruded the beam this way and then walked on it like into the page, bending about that axis, we want to know this distance and this distance. So we'll get the equation. We're looking at the IYs here. 9 inches to the fourth plus 0.36 inches to the fourth plus area inches squared times CGY, which is 3 inches, minus our CG total Y, 2.079 inches. I should be using the same notation constantly, but I'm not. All that squared, plus the last term, which is area, 7.5 inches squared. Oh, it should be squared, sorry. Times CGY, 0.5. Minus, where did it go? Yeah, the same thing here. Okay, so now we have this equation to find out that bending moment. So give me a moment and I'll calculate this. And after going through this effort, I sure hope these answers are correct. I'll let you know if they are. I'm known to make mistakes on occasion. 0.75 times 0.5 minus 2.079. Double checking. Okay. I get as our grand answer 15.944 inches to the fourth. There, one answer. Now, let's do the other one, IY, or IX, sorry. We have these guys, we'll add those up. 0.625 inches to the fourth plus 1.78 inches to the fourth plus 3 inches squared times Here's like our CGX 0.25 inches minus our total of here, which was 0.9868. Note that it's convenient that since it's the difference between these two here, and that since you're squaring it, it doesn't matter the order here if it's positive or negative. You're just looking at the absolute difference and then squaring it. If you ever get an I that is negative for either a subshape or for a total shape at all, I is never negative, ever. So the only case that it might be, for example, hint hint, is if you were solving your homework like this problem. You don't have to find I for this problem, but if you have this negative included shape, you would use, when you're doing the math for this one, you count the area of this little subshape as negative, and you would count the I as negative as well. But for like an actual solid object, I has to be positive. Back off the soapbox, and onto the other soapbox. Have the area for the second shape here, 1.75 square inches, times, okay, what was that thing? CGX 2.25 inches minus our total, which was 0.9868 inches squared. Give me a moment to compute that. All right, so 0.0625 plus 1.78 plus 3 times the difference between 0.25 and 0.9868 squared plus 1.75 times the difference between 2.25 and 0.9868 squared. Double check my stuff to make sure I didn't type in anything terribly wrong. And I get 6.2, I'll write it a little bigger, 6.26 inches to the fourth. So, that's how you would find the moment of inertia in both directions of a shape like this. Note that this would be called angle iron, and it's nice because you can actually get pretty reasonable I's in both directions without using too much material by just like bending something or welding something together right there. If you only had, say, this like one sheet like this, remember how terrible our I's are? This thing, that's super flimsy. You don't see beams made of like flat sheets of steel like this because they bow up and down very easily. So that's why you'll see shapes like angle iron, you'll see shapes like I-beams, which take advantage of the same effect of having a good amount of material in both directions without wasting a bunch of material by having a really big area. Like just a solid like square like this is pretty much like the most inefficient that you're going to get. Or actually, I take that back. A circle is the most inefficient you're going to get. The material here, all in the middle, contributes nothing to the stiffness of a circular beam. Okay, that is enough pontificating for now. I'm going to check these answers, make sure that I did this problem correctly, because I didn't do that beforehand. And please get in touch with me. I have a phone number that I've posted. I actually have it in front of me because it's a Google Voice number. So please use that if you're having issues. I've received calls from a few students, but not as many as I would have thought. So please, if you're having trouble, get in touch either via the ATIs or the phone or email, anything, as I'm here to help. That's what you guys pay for. Thank you.